Hello all, welcome to this GMC 310 little bit of revision of the introduction and the coordinate systems. I'm sorry about the lateness of this, but I couldn't get it out earlier. I was overcome by a thunderstorm and I couldn't hear myself thinking in front of my computer. Just to give you an indication, this is what it looked like. And I can assure you it was quite frightening. And also there was some damage around us. Fortunately I had none of that. Okay, so let's get into our lectures. The first thing, we had a little bit of an introduction where we looked at the Earth in context. Now it was just general things. It's not really stuff that you need to know. It's all about distances and how big we actually are. The Earth from the edge of the solar system. It's just to give you an indication of this orbiting planet that we're working on, and give you an indication also that of everything that actually moves and what the size of things are, and a context of where we're sitting. As I said, not much to learn here, so it's not really something which you have to worry about. But after that we got into the more nitty-gritty of the story, and we had a look at our coordinate systems and parametric equations and that sort of thing. So that was a little bit more daunting, I think. You sort of can remember. I think some of you are still busy with this, one of the assignments. And there we had the Earth systems and the Earth eccentric, Earth-centered, Earth-fixed system as well. First we had a look at what the Earth looks like. Obviously, you all know by now it's irregular, and you all know that we approximate it by an ellipsoid. Now, what do you need to know about the ellipsoid? You need to know that it's got an A and a B axis, and you also need to know that if you look at it from the side, it looks like an ellipse, and if you look at it from the top, it's actually a circle, and it's got a semi-major axis A and a semi-minor axis B. So, and you don't have to worry about the equations. You can remember the 1 over F. Normally it's termed as F, which is A minus B over A, but that comes into the formulas later on. There's some ellipsoids, just to give you an indication of how big they are and what sizes and how they differ. The ones important to us is the modified Clark 1880, which we used in South Africa until 1994, actually 2000, and WGS 84, which we've been using ever since. And you need to be able to transform between the two, because a lot of the stuff is still on the old Clark 1880, and while we were working on WGS 84 presently. Coordinate systems 1, the spherical and ellipsoidal coordinate systems. You know what latitudes and longitudes are. Don't worry too much about heights in this part of the course. We'll get to heights a little bit later on, but for now we'll ignore them, and we're working on an ellipsoid on the surface of the ellipsoid, as if we on there. Then we went to the coordinate system, the second system, your three-dimensional Earth-centered, Earth-fixed system, with an X and a Y and a Z coordinate, and the X coincides with the Greenwich meridian and the equator. Y obviously is 90 degrees to that, so that goes through 90 degrees east and the equator, and the Z-axis is coincidental or coincides with the axis of rotation of the Earth. Then we had the coordinate mapping system, another coordinate system, mapping systems. You know your conventional system, the X and Y mathematical system. Our mapping system works very much like it, except we now work in northings and eastings. Eastings in your GIS works very much like your X-axis in your conventional system, and northings like the y-axis, except the difference is we measure angles clockwise from north. So that's the only difference between the two systems. Then we did transformations from latitude and longitude to the Earth-centered Earth-fixed system, which is important because the Earth-centered Earth-fixed system is the system in which most things are measured on the Earth. And the formula are fairly straightforward. You've only got one radius of curvature, which is the radius of the sphere, and then you've got cos phi cos lambda, cos phi sin lambda, and sin phi. And your inverse transformation is y over x for lambda, and for phi we've got z over the square root of x squared plus y squared. Both of them under the square root. So that's not too difficult, I should think. Just have a look at the ellipsoid again with some formulas, especially V, which is one which we'll use a little bit later on, and it uses delta, which is over there, and the phi again. V is dependent on phi, you'll see that. None of the others, not C, not epsilon squared, not delta, nor F, nor N is dependent on your latitude, but V becomes dependent on your latitude. So that's important to realize or to remember that difference. Radii of curvature. Now, since we're working with the ellipsoid now, we're not working with a sphere anymore. We've got different radii of curvature. One in the meridian, which goes like that radius of curvature, and one in the prime vertical, which is the radius of curvature over there in that big circle, or that great circle. And you'll notice it's all these radii of curvature is dependent on latitude, so they all change with latitude. As you can see, V sits in there and V sits in there as well. Simplified, the radius of curvature looks like that. Yeah, that's your Earth-centered, Earth-fixed in the ellipsoid. Again, radius of curvature, and radius of curvature in the prime vertical. Not really, it's just a change in the radius of curvature of the prime vertical, yes. We can simplify the radii of curvature by C over V for n, and C over V for n, and then B over V for that n times 1 minus epsilon squared. So that makes it a little bit simpler. And then your inverse transformation is lambda is y over x, and phi is z over, and notice there that 1 minus epsilon squared sits outside the square root. It doesn't sit inside the square root there, so you need to remember that one. Then we had some convenient symbols again, just as a summary of all these symbols that we use. And we had a bit of a definition of a datum. What is a datum? Defined geodetic reference ellipsoid with a defined orientation. So it's two things that a datum adheres to. The ellipsoid is defined, and the orientation of that ellipsoid in space is defined as well. So if you've got two datums, and say you got a starting point for datum 1 over there, and you calculated it, because of the starting point and because you're working on the outside of the Earth, you actually define a center. Similarly, for datum 2, you define a center. And these things are not necessarily the same. That's why we must be able to do a datum transformation. So when we change datums, we have a datum 1, and the order then shifts with a dx, dy, and dz. And because we're working with Earth-fixed datums, your x, y, and z coordinates, which is fixed to the latitude, or to the equator, and to the rotation axis of the Earth, you don't have a real problem of rotational axis about the rotations about the axes, although there can be. So you may or may not change the ellipsoid from, for instance, Clark 1880 to WGS 84, and there may be rotations about the 3 axes and a scale change, but that's something for a later stage. And after that we did a little bit of coordinate transformations. There was specifically an assignment that you had to look at, and that assignment looked like this. You have a practical A, which have a point and spherical axis, spherical Earth with a radius of that, transform to another spherical Earth with the same radius. So it's only your translations which are applicable. And then you got a practical B, where this is now a little bit more complicated, where you have to go from the Clark 1880 ellipsoid to the WGS 84 ellipsoid for the second. So there's 3 translations and also a different ellipsoid. But we'll do that practical in the next. I'll show you how to do it in the next video. So that concludes this video, and the next video should be up shortly, early tomorrow morning, I think. Well, I don't know when this one is going to be on ClickUp, depending on when Cameron wakes up. Okay, bye.